the slides that I'm showing, periodic table. And from here, we will see that on the periodic table right now, there are 108 elements. Those elements including a very stable one and a very unstable one, all included there. When we were a student like you guys, I mean, in the school, then we used to know there are only 105, but now you will see on the periodic table, if you look, you will see 108 there. So new elements are being discovered or found in the lab. Elements means it has to be unique. It has a certain number of proton, not like others, right? So these type of elements are found. Maybe in the future, who knows, there will be many more. And in fact, for some, in future that the elements will be discovered, will be put here. Why? Okay, it will be put in these places. This is Nihonium, Moscovium, Tennessinium. So in this way, because neonium in Japan, there are 5 different labs in the world there where you can do this type of fundamental research. They have this type of instrument to do this type of fundamental research, because it needs a very specific, very sophisticated, very I don't know it's big or not, but this sophisticated advanced machineries in the world. There are 5, 2 in US, 2 in 1 in Russia, Japan, Germany, this type of places only. So only those from there, those labs, the elements will come out, and that is why the name, the element's name will follow the places probably that they will be developed. Okay, so we already have seen in the periodic table that this periodic table we can divide into few blocks, S, P, D, and F. F is, we will not discuss the F one, but S, P, and D block. S, P, and before that, once again, these are the groups. Yeah, once again I said, so these are the group here, group 1, group 2, group 3, and so group 13, 14, in this way group 18. So this way the group is increasing this way, right? Group increasing this way, and this is the period 1, period 2, period 3, period 4, right? So in one group, like this group, the elements are having similar characteristic. They have similar characteristic. Of course, they are different, but having similar characteristic. In one group, in one period, they will have the same principal quantum number, that is number of n, right? That is principal quantum number, but they will have, of course, different number of electrons. So this is the difference between them. This is the one difference between them, but if we want to categorize them to know better, to find out where we can find them faster, easier, we can divide them, or we can categorize them into 3 different blocks. There are many more. I'll show you in a bit, but usually S, P, and D block. And S, P, and D, this name came after the outer orbital, that is their valence electron shell. That outer, the last orbital they have is the P. Those elements here, they have the last orbital is P. Those elements here, they have the last element, orbital is D, and here is S. So in this way, we can also different group, we can put them into different block, actually not group, block. Okay, and because of this type of electron distribution, configuration, and their position on this periodic table, their characteristic changes. Okay, their character will be different. How do we know what will be their character, and how can we find what will be the character? Are these, that atomic radius, of course, it is increasing to a certain, I mean, from hydrogen is the lowest atomic, yeah, then it will increase more, of course, and then it increases atomic radius, melting point, electronegativity and electron affinity, ionization energy, all those things will also be increasing or changing according to their configuration of electron configuration. So now if we look here, the atomic radius, it is increasing when we go from left to from top to bottom. If we go, the atomic radius is increasing, because we know that when here it is hydrogen, right? Let's say hydrogen, only one electron it has, and then it is what is that? Lithium, right? So it has 3. And then sodium, it has 10 electrons. So in this way, when we're going down the periodic table, the number of electrons are increasing. Okay, if I leave it there, my microphone, is it clear? Can you hear me, or do I need to hold it to near to my mouth? Can somebody tell me? I cannot see your chat box. If I talk in this way, because my microphone is not, I'm not holding my microphone to my mouth, is it still clear? Can you hear? I cannot see your chat box, and if I close this, I have to draw it once again. So can you, somebody tell that whether you can hear me?
Yes, it's clear.
Okay, thank you. Okay, so the atomic radius is increasing because I am going down the periodic table from top to bottom is increasing. We understand that the number of electrons are increasing, their size is increasing in that way. But what we don't understand that from right to left to right, if we go, the number of electron will also increase. Yeah, the number of electron will also increase, because here the first one, let's the first group and first period is hydrogen, and then it is the helium. Hydrogen has only 1 electron, helium has 2. So in this way it is increasing as we go to the right side, and then from here is lithium, and then it is in neon. It is increasing in this way. So lithium has only 3, neon has 10. So it is increasing also. So when we go from left to right, as the number of electrons is increasing because the number of their proton is increasing, right? Number of proton is increasing, or their atomic number is increasing. That is why the electron is also increasing. I'm telling about the electron because the electron is the outer side, and it is determines the number of size, right? So since electron is increasing from left to right, it was supposed to, the size of the atom was supposed to increase, but it is the opposite thing. If we go from right to left, the size of the atom is increasing, and when we are going from left to right, the size is actually decreasing. This is one interesting thing, because it is due to the gravity, or it is due to the when the number of electron is increasing, as I just now saying, the proton or atomic number was increasing as well, right? When there is 3 protons here, 3 electrons here for lithium, and when there is let's say fluorine, 9 electron, so 3 electrons means 3 proton, right? Sorry, not proton, almost going at Yeah, proton. Yeah, we call it proton. The positive charge in the nucleus, we call proton. So the lithium has 3 proton in its nucleus, and fluorine has 9 protons in its nucleus, right? So now 3 protons, 3 neutron, lithium has, and 9 proton, 9 neutron, fluorine has. So since this electron, the nucleus is the most and condensed matter or condensed energy is condensed there, the number of proton is increasing in the nucleus, the mass number is increasing. It becomes more dense and dense and dense. Because remember that in one period, right, in this whole period or this period or this period, they have the same electron configuration or this type of number. Main principal quantum number n is same. If n is 1, all of them has n equal to 1. If n is 2, for them, they have all n equal to 2 for number 2 and 3 and so on. So the elements or the particles, let's say electron, neutron, everything we call particle. For lithium is this big size, for example, this big size, and it has 3 proton and 3 electrons. And fluorine also almost similar size because the principal quantum number is Sem, and in this same size, almost similar size, it has more number of proton and neutron. So when it has fluorine has more number of proton and neutron, that means the mass inside it is increasing more. The fluorine becomes more dense, more heavy, and since the nucleus, the proton and neutron are the nucleus, right? Proton, all the proton in the nucleus. So since the fluorine nucleus becomes higher and heavier, and it is positively charged, neutron does not have any charge, it is becoming higher. So it will attract the new electron all around it more strongly. It will attract it more strongly than lithium one, because lithium has only 3, fluorine has 9. So for 9, it is much more stronger than 3. Is that right? And that is why, since the attraction is more for fluorine, I'm talking about fluorine, but as we go to the right side of the periodic table, since it is bit more, they are compact. On the right side of the periodic table, they are more compact and dense, so that their size actually decreases. Even though the atomic number increases, the size decreases because of that. Okay, and this characteristic will also explain the electronegativity and ionic and ionization energy and so on. So we will talk in a bit about those, and we'll say in this. Okay, so ionization energy, melting point, I'll come in a bit here. For ionization energy, let's say ionization energy is the energy that we need to have to remove one electron from the outermost, the last one, the last orbital it has. If we want to remove one electron, right, from the outermost orbital, the energy we will be needing is the ionization energy. It's called ion. Of course, the element should be in the gaseous form, not in liquid or metallic form. So it will be gaseous form. Let's say this is one nucleus here, and this is one orbital. This is N2, this is N3, something like that. So in gaseous phase, I want to remove this electron. Okay, this is an electron. I want to remove it because the electron will be attracted by this nucleus, and I want to remove this electron from here. How much energy do I need to give or to provide to that atom so that it will at it releases this electron. And that is called the ionization energy. And ionization energy is positive always because you have to provide the energy there. And this is electronegativity. Electronegativity is how much electron it is attracting towards it is the electronegativity. On one atom, how much energy it will be attracting to itself electron to make a bonding towards it. And there is no scale for measuring the electronegativity, but Linus Pauling, he made a scale that fluorine is the highest in the electronegativity. Is called 4. Fluorine was given because fluorine it attracts electron from anyone around it, so it attracts the electron very strongly, and that is why it was given 4. Okay, and based on compared to fluorine, the electronegativity was measured all of other elements. And after fluorine, there is oxygen, and then chlorine, then nitrogen, and so on. Of course, the halogens are higher, usually higher in this electronegativity. And electronegativity increases when we go from, again, the same way, when we go from left to right, or bottom to top. Okay, we go from left to right, or bottom to top. And this electronegativity as well explain, the electronegativity characteristic of the elements as well explained by this atomic radius, how this atomic radius is small. So when the atomic radius is smaller, that means it has more electron density in it, nearby it, and it is able to pull more electron. And since it is smaller, the size of the atom, the size is small, but inside that atom there is a very thick, dense, heavy nucleus, so that it can attract more, and it is not bigger in the size, so it is easy to manage the electron or hold the electron nearby. And that is why that way it can be, the electronegativity can be explained in that way. So electronegativity increases from left to right and bottom to top, or it will increase diagonally when we go from top bottom left corner to top right corner. In that way, it will increase as well. This way, the trend goes like that. Melting point. Melting point is when the bond is broken between them. Okay, bond is broken, and you have to add more energy for a bond to be broken. And there are a few other things to consider here: the structure, the crystal shape of it, or different type of bonding it has within them there. So for the transition metals, we see from here the transition metal, they have certain type of structure, atomic structure, or lattice structure, or crystal structure they have. And these structures, breaking the structure first and bonding between them is very high. It takes a lot of energy for them to break those structure, and that is why the transition elements, they are very hard to break. All right, and that is why the melting point is quite high for them. But for non-metals, right here, for non-metals, usually they have their structure is very simple, not that complicated for them, and it is even though they are bonded together, in between them they are weak bonds. They make the weak bonding between them, and that is why it is easier to break them. There is a difference, of course. There, chemistry is all about exception. There is exception as bromine and carbon, of course. There we can also describe that one or explain that one due to their atomic structure as well. Okay, so this is predictable, the trend, so the predictable, and since we are talking about the structure and they form the structure, right? The bonding, we will be talking about the bonding tomorrow, because tomorrow we have class, right? So trends in atomic is radii is a short form of radius. So atomic radius, the atomic radius increases when we say that it decreases, right, from left to right and bottom to top, it decreases. So it increases. Why does it increase then? Well, the same opposite logic or opposite explanation, that when we go from here to here, the principal quantum number does not increase. That means essentially the shape or size is almost same, but they have more and more atoms or atomic number. But when we go down this periodic table, right, from top to down, bottom, then what will happen is their principal quantum number will increase. Here is 3, here is 4, here is 5, here is 6. In this way, it is 7. So 7s, 7p, something like that. So when there is 7s, or the principal quantum number is more, that means there is already, if there is, how do you say that, 1s, right? Only 1s. If we have 2s, then 2p will come along. If I have 3s principal, then 3s, 3p, and 3d, it will come as well. That 3d will come. So in this way, the number, as we go down, the availability of their options for them to expand is more, and that's why electrons are expanded more, and the number, principal quantum number, increases. So that's why it can have a bigger space, to house all the electron it has, and that is why the atomic radius increases. Once again, the same thing, you see that here in 7s, cesium, beryllium, titanium, lead. So in the same period, we see cesium is the biggest, right? Cesium is the biggest, and this, it reduces as we go on right, even though the same, because as we go right, the number of electron is increasing. Number of protons are increasing in the nucleus, and the mass of proton of the nucleus is increasing, so it can hold or it can attract the electron more strongly, so it becomes compact. So even though it's the same principal quantum number, it has a smaller radium. Radon has more smaller size for this. If we want to see that on a chart, we plot this trend of increasing or decreasing of the size of electron, not electron, is nucleus, we can see that, okay, it is increasing, bigger size, then it goes to fluorine, is reducing the size. Sodium goes to chlorine, its size is reducing. Potassium going to bromine, the size is reducing in this way. Okay, so this is the same thing. this is the same thing that is increasing. I mean, what do you call it? That just now I was talking about why it should be. But when there are some what do you call it, densities, ups and downs here and there. So if we make it bigger, or if we elongate it, I didn't elongate it here, but if we look at it from when we are going from let's say potassium, where is potassium to bromine, here all the elements are not shown from this period, but what do you call it? If it was shown, it would be this. We could see that it is not always the same trend. Like it is not always the same trend that is smoothly going down. It is there is ups and downs here because the number of electrons, the shells are increasing. Okay, so maybe here is 3s, and then this is 3p is here, or 3d is here as well, and that is why to house those electrons 3p 3d, right? So this becomes a little bit bigger, and then when 3d, after 3d is going, it is decreasing as well again. So that is why this is ups and downs here, we can see. So the explanations that we have already talking, why it is increasing and why it is decreasing. As going across the period, atomic radius decreases because the atomic number increases, and nuclear attraction force, because of this heavy nucleus, is increasing. The additional electrons are added to the same electron shell, but electron shielding effect is similar. Shielding effect again. If we want to talk about shielding effect, I still have time something. So when we are talking that this is what do you call it? Nucleus is too big. I need to make it smaller, otherwise the size of the atom will be bigger. So let's say this is a nucleus, positive. This is a nucleus, right? And then there is first orbital, second orbital, third orbital. All right. So here two electrons, each orbital, let's say each orbital, we show it by Bohr's model. Oh, I need to talk about the modeling, yeah, of the atoms. I'll talk about. So just show about the Bohr's model that electrons are here, 1, 2 electrons here, 2 here, 2, and of course here it will be 2 or maybe more than that, let's say. Yeah. So what is happening is, for this electron, our electron of interest for our study here, which one should I take this one? So this is our electron of interest, right? Here it is, it will have that. Oh, this is the nucleus. This is the nucleus, okay? It's supposed to be at the center. And this electron, they will have some attraction, they will feel attraction, they will feel attracted to the nucleus. It will feel attracted to the nucleus. It will feel attracted to the nucleus, right? Everyone will feel attracted to the nucleus because all electrons are same. All are the same because there is no difference because of this electron and that, all of them. Only their position is different. Okay, so each of them and every one of them will feel the same attraction, not same attraction, attraction. But for it will also feel the attraction with the nucleus. But the problem is, because of this electron, and this electron is not stationary here, it is all over in this region, right? In this region, it's all over. So what will happen is it will make a shade. It will create a shading for this electron to be able to be attracted by the nucleus. It will feel a shade. It will be shaded by other, not only for this electron, for these all of them will will circle, or it will, all of them will cover the nucleus in a way that the outer shell electrons, they will be a little bit shaded. All right, they will be shielded from having a fair share with the nucleus. So that is called electron shielding. Okay, for the electron shielding effect. And the higher is the shielding, the easier for an electron to be removed from the atom or the atomic structure. So that is why if this electron has to be removed, it is easier to be removed, because if there are more electron here nearby the nucleus to be shielded, and it will be easier for it. And now now what do you call it, imagine that it is a big molecule, sorry, not molecule, big atom. The size of the atom is very big, and also the number of electrons are very too much. So what will happen is the electrons are so easy to be replaced. Same thing goes on here for the cesium, right? It's very big, it has more electron, and that is why the outermost electron is so easy to be replaced, I mean removed from here. And that is, I mean, that is the one thing that the shielding effect happens. Okay, so we can show the shielding effect. We can study the shielding effect by ionization energy, but we will not just do it now. We have to finish other things. Number C, the effective nuclear charge increase as and pull the outermost shell closer to the nucleus. So when that effective nuclear charge increases, so that the effective nuclear charge means the power of nucleus increases, the power of nucleus or the force of nucleus increases. So that is why the effective nuclear charge will increase, and it will try to hold strongly the outer shell electron closer to the nucleus, and that is why it is smaller. Okay. Explanation 2, as we go down a group, atomic radius increases because the atomic number increases, but the shielding effect is also increases. Just now I was telling about the cesium, right? The shielding effect for the cesium will also increase, and that is why the outermost electron for the cesium, it is very hard for the nucleus to pull it down. It cannot have that. The effective nuclear charge reduces, and that is why it is far, right? Okay. All right. So far we are talking about the trend in the periodic table. And in a simple slide, if we want to summarize this thing, that atomic size increases from right to left, electronegativity increases from left to right, and then ionization energy as well increases from left to right, because ionization energy and electronegativity is the energy it will be required to remove one electron or attract one electron from one atom, so it will be increases. And the same thing, the similar trend, the same trend goes another way from top to bottom or bottom to top. This. So now we are electron ionization energy. If we want to talk about the ionization energy, and if we want to see the ionization energy put it on this graph, right? Ionization energy. I'll show you ionization energy in a bit exactly. So there are what do you call it? Second group, sorry, second period. Second period elements from the second period. First period is hydrogen and helium, right? Yes, the helium. First period. Second period, we started with lithium, then beryllium, then here is boron, then nitrogen, carbon and nitrogen, all these things. So this is the second period elements if we take, okay, and want to see the ionization energy for this. I know that this slide is not, you don't have this slide, but don't worry, it's just to explain the thing. So second period elements we have taken and then put it again on a graph to do the graph to compare the ionization energy. What is happening is beryllium, the first ionization energy. This is the first the blue one is the first ionization energy. First, second, third, and this is the fourth ionization energy. First, second, third, and fourth. This is 3, yeah. And so 1, 2, first, second, third, and fourth. What is the first, second, third, fourth ionization energy? Why so big? First ionization energy is this is nucleus. So this is the electrons around nucleus, right? It's around the nucleus. So if we take out this electron, it will be first ionization, right? If we take this electron away from this, so what will happen here? We have 3 electrons here left. Let's say this is 4 electrons are here. So if we take one away, we will be left with 3 electrons here. Now, if we take 2, right? Of course, it is easier to take out the outermost one. If we take 2, so it will be second ionization energy, and then third ionization energy, and fourth. So what is happening is the more you are taking, if you are taking 1, it still has 3 electrons, and the nucleus is positively, although it's positively charged. Although it's positively charged, the nucleus, it has 3 electrons, so it is okay, or at least okay, just 1 gone. What's the problem? What's the problem? Not a big deal like that. If you're taking 2, then it becomes concerned that, okay, you have taken 1, I cannot give more like this, because the atom becomes more and more positively charged. I mean, it is not a neutral anymore. It is losing its neutrality and it becomes growing positively more charged. When you are taking the third one, and since the positive charge of the nucleus increasing, it is holding the electron that is negatively charged more closely or more strongly, or the force is increasing, right? If you divide the force on this 4, and if you divide this on 2, of course, the force on 2 is more higher. So when you are taking 1 away, the force is still okay, and then taking 2 and then 3. And the last one for this case is the 4th one, right? It will be the most hard to remove, because the nucleus will have no other thing to be to hold to. It will be nothing else around it, and it will. So that is why the 4th one is very hard, and that is showing the 4th one is hard. So for beryllium, we see that first ionization energy is low, second ionization energy is lower, then third is also okay. I mean, not okay, of course, but is lower than 4th one, right? Okay, this is a question for you. What is the difference among them? Among these 4, there is no marks on it, but I want you to reply. Don't talk, don't type, talk, because I cannot see the chat box here. I'm on the full screen for this presentation, so I cannot see your chat. So anybody wants to chip in that or try what is happening, what is the difference that you can see here? Or do you see any problem here, or do you think there is a problem? Anyone? No? No problem. Okay, so I don't need to, there's no problem, so it's okay, let's go then. Is it? For beryllium, we see that beryllium is here, right? It has four, atomic number is 4. Beryllium has 4. Bromine has 5. And then carbon and nitrogen has 6 and 7. So 4, 5, 6, and 7, right? So what is happening for beryllium, that first one, because it has only 4 electrons, sorry, 4 electrons and 4 proton in the nucleus, 4 proton and neutron there. So you take out the first electron, it is not very high, whereas for nitrogen the number 4th one is higher than that because it has 7 protons. So it is higher because it can hold, or it can take the electrons more strongly, or the force, atomic force is, nuclear force is higher. That is why it is higher to take. For second, also the same thing. For third one, for beryllium, beryllium becomes concerned when the second electron was taken away, but when the third electron is taken away, it becomes very, very concerned, and it is too much because it does not want to give this third one. It already has given. It has only 4 and it has given already 2. It does not want to give third. So the 4th one, of course, it will be high because there is nothing else. And there is only 4. The nuclear force is 4, so it's, of course, it is less than 6 or less than 7, of course, and that is why it is about 20,000 nuclear force. Okay, not 20, 22 or 21,000 probably. It is there for 4th one. For boron, it has 5 electrons. So first one is more than this, or almost similar to that. Second, also a bit higher. Third one, it does not mind that much as this beryllium did, because it still has 2 other electrons to be taken or to hold to. So third one, it doesn't, not that high. But 4th one is very high, higher among them, because it has 5 proton and electron in it. Proton and neutron in it, and then it can exert more force than 4-1. So 5 is bigger than 4. That is why it is exerting. You have to put more effort to take from here. For carbon, again, for carbon, you see that it has 6. So the first one is easy to take. Second one, of course, it is almost similar and more than this actually. Third one also a bit more than that. 4th one is not as high as this because it has another 2 to take. Of course, the 4th one will be very much higher. 6th one will be high, much higher if we go. So this is the trend for carbon, for ionization energy for the elements. All right, now let's move to the metallic character. Actually, I don't need to put in my ear because you guys do not talk. I can just hold it here, right? Okay. So metallic character, the elements is increasing the transition metals. We call the transition metal in between this 3 to 12 in modern periodic table, 3 to 12 groups. Okay, so So there is the transition metals are called in this side. They are, remember, they are d block elements, and for them it is if we they always try to remove the electrons at the outer skirt or outer shell they have. They want to remove that electron, and by removing them, it is easier for them to remove the electron to be more towards the noble gas. Electron is, what do you call it, noble gas configuration. For them, they want to be, everyone wants to be to noble gas configuration. So for them, it is easier to remove the electrons from outer shell, and that is why they have metallic characteristic, because we call metal them because they remove the electrons from their side. Okay, they try to be oxidized. They're easy to be oxidized by losing the electrons. State of matter at room temperature, and they form the metallic bonding as well. Sorry, they form the metallic bonding by the, actually it should be lanthanide, actinide also here, and this, because we do not know much about them here yet. So the metallic, they will form the metallic bonding. We'll see what type of bonding are these later on. So they will form the metallic bonding as well. State of matter at room temperature. At room temperature, all the elements are either gas or solid, but only two elements are liquid, that is mercury, highly carcinogenic, and bromine. All right, they are liquid at room temperature. Okay, so all other elements are either solid or gas. Mostly the non-metals are gas. All the metals, they are solid at room temperature. For francium, francium has been discovered in 1940. It's not very long ago. It's 1940, I think. Yeah, it was discovered. But the problem is francium does not have much of it. It has not been studied. Many of these characteristic of francium is not known, but it is put here because it is very easy to be oxidized. It's very, very easy to be oxidized, and there are so many isotopes of francium, but the most stable one, all of them has a very low some few seconds. All of them are milliseconds. They have their what do you call it, lifetime. But the strongest or the most stable isotope for francium was found in 223. All right, francium, and half time for this is 21 minutes. If francium would be, it is supposed to be, it is going down in this melting point, okay? The melting point is going down in this way. And if we could find the melting point of this, I mean, for this francium, could do it, if it were stable, yeah, that's the good word. If it were stable, we could find out what is the melting point of it. We would find it about room temperature, like 22 degrees centigrade, right? It would be 22 or 23 degrees centigrade. It would be liquid, but since we don't find it, it is not stable. It doesn't stay in the for a long time, only like 20 minutes, right? So yeah, it is very hard to find. Okay, so we are done with that atomic structure, but let me just tell you a story about finding the structure of atoms that I should have told before, but I forgot. The structure of atoms, where is it? Where can I put? Okay, periodic table, structure, atoms. Okay, so not hydrate. Let's say we are talking about the structure of atoms. At first, when it was discovered, we don't have much time to do the storytelling, but from the very beginning, we used to know, or the scientists used to know, that there is something called, if we break a particle down or matter down, we will reach to a point where it is undividable anymore, undivisible anymore. Okay, so Dalton, he started with this, that it should be called atom, because it came from the Greek word iota. So it will be called atom, that we cannot break this atom anymore. And later on, it was found that no, atom itself can be divided, it can be broken, and if we break it, we will find some other particles. So for a long time, the scientists were trying to understand what the atom would look like. And you can imagine that just not few hundred years, just 100 years ago, it was confirmed just 100 years ago how the atom, and we understand the atom is so nicely that there is electron, proton, neutron, this look like that. But just 100 years ago, like our grandfathers, they did not have ideas of how the atom looked like. I don't know what they would think. Right, we know it very good. We don't have to write it down. It's already established, and we rarely talk about it. That how does the atom look like? We don't talk much about it. But what our grandfathers, great-grandfathers would think of how an atom looked like, I sometimes are actually surprised that I think that what do they think. So before that, J.J. Thomson, he started to think about the structure of atom, and then he thought that, okay, there is a plum pudding model, right? So this is in center of a plum pudding model. This is the pudding in a center. This nucleus is at the center, something, and then electrons are attached as a plum on this pudding. It's a cake. It's a cake like in a ball, and in that cake there is a positively charged nucleus, and all around it inside that cake their electrons is scattered in that way. But it does not actually explain the structure or characteristic of an atom or matter much. So what the Rutherford came out with or we call it planetary model, right? In 1913, I think 1914, 1911, something like that. So in 1911, yeah, Rutherford came out with a planetary model that, okay, almost correct, Rutherford, that we have a nucleus at the center, but the electrons are rotating against it, just like the sun and moon and the stars orbiting, or our Earth and other what's called that planets are orbiting around the sun. So that is how they move. It is Rutherford came out in this way, in this idea. To get to this idea, they did a gold foil experiment, right? One alpha particle was bombarded against a very fine, a very, very thin gold plate, very, very thin. It's 10 times thinner than your hair. So it was bombarded, and there were some detector was put against all around it. Okay, some detector were put all around it to detect how much of this particle comes back, and it was found that only few of the particles came